Good afternoon, everyone. Thank you, Alex, for organizing this very, very exciting and very interesting session. My talk is going to be focused on the idea of identifiability in brain connectivity and how we can borrow that term and actually make very exciting questions about how brain and brain connectivity develops and whether we can disentangle different traits that are more heritable versus more due to shared or unshared environment. As we probably all know in this room, our main two sources in brain connectivity of data is the so-called structural connectivity and functional connectivity. The first part of my talk is going to be focused on functional connectivity. The second part, I will combine structural and functional connectivity so that we distinguish information that is mostly coming from heritable traits versus environmental-related traits. So the idea comes from this, in my opinion, pioneer paper by Emily Finn and colleagues, where they put on the table the idea that we're reaching the era where the quality of fMRI data give us the opportunity to show fingerprints or characteristics of different subjects that keeps happening in a test-retest fashion. So basically, the idea is very simple. If you allow me the metaphor in mind, you have two decks of cards, except these cards are special. They are actually whole brain functional connectomes. And then you're going to take one card and you're going to tell me, Joaquin, go figure who is this same subject in the other pile of cards. The piles of cards are representing tests, retests, or acquisitions that happened usually in different days, but in a small period of time. And the better I can do that job, it will speak better of the data set because it will speak that I'm finding characteristics of the subjects in, let's say, day 1 that were actually reproducible in day 2. When I'm playing this game and I'm failing very frequently, this speaks low either of the data, the acquisition, the task design, the processing, on a number of things that is difficult to disentangle, but basically that will give us in a very bad position where we don't have characteristics that are reproducible across individuals in a test-retest fashion. So basically, the way this game works is I will take a functional connectome and I need to figure out in the, let's say, retest pool who is the same subject. So basically what I'm going to do is I'm going to compare the functional connectome that I'm given with each and all the functional connectomes of the retest pool, and I'm going to develop a very simple similarity score, which is simply going to be the Pearson correlation coefficient of the entire functional connectome that I have in my hand versus all the ones on the retest too. So as you can imagine, I could make a bar plot where I could measure what is the similarity between the question mark subject and all the other subjects in the retest pool. And given this data, I will argue this is probably subject 4. Now, depending how often I am successful in my choice, I will have a higher or lower identification rate. So identification rate is reflecting the relative number of times that I'm successful when playing this game. We try to elaborate another measurement that is a little bit more continuous than this one. In this one, I could argue you're giving me just one shot. I say subject 4 is successful, is not successful, and then we move on to the next functional connectome. But what if it was not subject 4, but it was subject 12? Well, okay, it was not ideal, but still subject 12 had a very high correlation in the retest session with respect to the first test session. And that's a very different scenario than if in reality it was subject 15, where I would have needed 20 attempts, actually the entire cohort size, to actually figure out who was the subject. So at the end of the day, when computing identification rate, you're actually doing all cross-correlations comparisons of the full brain functional connectomes. So in this work with Enrico and Miko, what we decided to do is, can we represent this into a matrix? Let's have a matrix where we put in the same ordering in rows and columns all the subjects, and the entries is actually the correlation of the whole brain functional connectome between all of them. When you order rows and columns in the same ordering, it's very interesting because the main diagonal has a very powerful meaning. It's actually for each subject in the cohort to what extent the functional connectome looks alike in the test versus the retest session. Any element in the off diagonal represents any comparison between any subject test and any other subject retest and so on. Keep in mind that this matrix is not symmetric because my functional connectome test versus your functional connectome retest will not have necessarily the same similarity than my functional connectome retest versus your functional connectome test. So once that you have this matrix, we wanted to be able to provide a score in the same spirit of the identification rate, where we could tell you, okay, your data has a very high identifiability or not. So we did something very simple, which is very intuitive. At the end of the day, identifiability means that we want a brighter main diagonal than the off diagonal of this matrix. In other words, the test retest of the same subjects should look alike more than between different subjects. So we propose this concept of differential identifiability score that is as simple as we're going to take the mean of the main diagonal, which we call I self, on average in your data, to what extent test retests of the same subjects look alike, minus discounting how similar are your different subjects in your data set. Just for convenience, we multiply by 100, and to give you an idea, if you have 25 points in your data set of differential identifiability, it means that your functional connectons of the same subject test retest correlate 0.25 more than between different subjects on average. Just to give you an example of 3 different scenarios where your data could be, and you want your data to be in the middle scenario here. Let's focus on the left. You got 2.34 points of differential identifiability. You don't see the main diagonal. There's nothing special about it. Actually, the problem here is that I self, the values on the main diagonal, and I others are very similar. It all looks the same, and you don't have any identifiability. If we go to the right side of this figure, you kind of see a little bit of the diagonal, but you still have a lot of problems because the test-retest values across the main diagonal are fairly low. So you kind of have the opposite problem. You don't have identifiability, but not because all the functional connectors look the same, but actually because even the ones that should look the same, they don't. You want to be in the middle where you got, in this case, 28 points in this small data set with 20 subjects, test retest. You have a much brighter main diagonal, which means that the functional connectors that you obtain whole brain in test retest of the same subjects are way more similar, actually 0.28 on average, than when you are comparing different subjects. If you know this movie on the bottom left, in the lab, when you have a data set like this, we say that it has the John Malkovich syndrome, where you could call the same subjects again and again, or different subjects. It doesn't really matter because all the functional connectors look alike. If you have the other syndrome, the mask syndrome in your data set, the problem is like if everyone that you recruit in your cohort is wearing a mask, you call it the next day and is wearing a different mask. So both are problems that I encourage you to check on your data, because if you are either on the left situation or on the right situation and you're trying to predict fluid intelligence, or depression score, or aging, or disease progression, or working memory performance, or executive function, you are in a very suboptimal situation with your data to actually be able to make mappings, associations, or predictions about it. Where you want to be is in the middle situation, where the characteristics of the individuals keep happening in the test and in the retest. So we didn't want to abandon you here with a score. We wanted to be able to provide a framework that maybe can uncover identifiability that is present in your data, but you were not being able to see because of the presence of noise and misestimations and head motion and all kinds of sources that produces that test retest do not look alike. So we wanted to provide you with a data-driven framework where you don't have to decide anything except having all your functional connectors, doing a procedure that I am about to explain, and hopefully uncovering identifiability in your data. So basically, what we did is something that is really simple. It's called principal component analysis. The only thing is that for the principal component analysis, we did it at the group level, where you have 2 functional connectors per subject, test, retest. We vectorize the functional connectors and choose 2 vectors where n is the number of brain regions, and we simply pair them for our convenience, test, retest, test, retest, test, retest, although it doesn't really matter for PCA because the ordering of the columns will not affect the results. So principal component analysis is going to give me a number of orthogonal components, twice the number of subjects because I have test retest, that are orthogonal to each other. It's a full explained variance method, and it doesn't depend on any simulation. It's analytical. So if I would use all the orthogonal components or connectivity modes to reconstruct the data, I will be exactly with my original data. Basically, I wouldn't have done any operation on the data. What we're going to do is we're going to start dropping the components that explain the least variance and the 2 components that explain the least variance and the 3 components that explain the least variance in an iterative fashion. We're going to reconstruct the data in absence of those components, and we're going to check the identifiability matrix and the corresponding differential identifiability score. So when we did this in a small data set of 20 subjects, we got a very nice surprise. I like to read this middle plot from right to left because at the top right, I haven't done any procedure on the data, and I have an identifiability of around 17 points. As we're dropping components, identifiability goes up. That means that the main diagonal minus the off diagonal is increasing. That means I am gaining identifiability. That means I am removing in a data-driven fashion from my functional connectivity data components that were avoiding that I am able to match test retest of different subjects. But equally interestingly, there is an optimal point after which I'm overdoing it. I am removing from the data information that was actually helpful to differentiate the same subjects from different subjects. And if I really overdo it, I could even get a smaller, lower identifiability than if I don't use the method at all. So this was a small example with 20 subjects. We went big. We used the 100 unrelated subjects from Human Connectome project, the 7 fMRI tasks available, and rest. And we saw that there is universality on this across fMRI tasks. Basically, it doesn't matter which fMRI task you're using. If you have functional connectivity data, you can just use our method to actually, if you want, clean or uncover identifiability in your data so that you can go to your next stage and make questions about executive memory or working memory performance or disease progression. So basically, we also saw that the method has universality with respect to the number of time points that you have in your time series. It doesn't matter how many fMRI volumes you have here, from as low as 50 to 1200. It's always worth it to use our method in the sense that it increases identifiability. The red plot here is the level of identifiability when you don't use our method across the number of fMRI volumes in resting state. The blue is always very much up top, which means that we uncover identifiability of the data regardless of the number of fMRI points. We decided to complicate ourselves. I don't have time to tell you in how many different ways we're complicating ourselves in this project, but I will tell you that one of the ways we did is using test-retest collected in different imaging sites. In other words, the worst nightmare of any fMRI engineer. Basically, we expanded the identifiability matrix so now you have within site 1 test-retest, within site 2 test-retest, and this is the challenging part. Test in imaging site, retest in imaging site 2, and the other way around. Basically, now you can imagine that I have 4 differential identifiability patterns to track corresponding to the 4 different quadrants. Long story very short, we're able to compensate the multi-center effect in functional connectomes. In other words, if you don't use our method and you are doing within site test-retest, in this data set you get around 30 points of differential identifiability. If you use the test-retest collected in different imaging sites and you use our method, you reach the same levels, even slightly more, of differential identifiability. For those very worried about global signal regression or no global signal regression, this method works in both cases. At the top, you see the results in no global signal regression when processing the data, and at the bottom, you see the results when global signal regression was used in the data. You can see, let me emphasize a little bit how challenging it is to get these secondary diagonals, because now I'm finding who is who test-retest when the subjects are the same subject in different imaging sites. You can see the effects of original data versus reconstructed, global signal regression, yes and no, and in a validation data set with the same subjects again, having a test-retest where we actually freeze, we keep the components that we learn from the orthogonal basis of the training data set. Okay, so at this point, if our method is universal for the fMRI task, if it's universal with respect to the number of time points in the scanning sessions, and if it's kind of universal with respect to whether you collect the data in the same imaging site or in different imaging sites, maybe we have some kind of powder that allows us to make deeper questions about the brain and how the brain develops. So in Human Connectome project, we are lucky to have a good number of pairs of twins, where now we're going to twist a little bit the concept of identifiability, and my test-retest can be either monozygotic twins or dizygotic twins. Remember that monozygotic twins search 100% of the genetic material, whereas dizygotic twins search 50%, as if they were siblings, but I will argue the amount of shared environment is much higher. So basically, the good news is that in structural connectomes now, when I'm measuring with Frobenius norm the dissimilarities, so now I want a main diagonal that is as close to 0 as possible, this method works. What does it mean that it works? It means that it recovers a lot of hidden, it uncovers a lot of hidden identifiability that is present in the data when not only you have actual test-retest, really 2 sessions of the same subject, but also when you have monozygotic twins, now it's not test-retest, it's really different subjects, or when you have dizygotic twins. We can look at this in very different ways. I can tell you that we're seeing the same effect in functional connectivity. Here on the left is structural connectivity, on the right is functional connectivity. Red line is actual test-retest, dark blue is monozygotic twins, and cyan is dizygotic twins. It is very interesting to see that I can argue that this gap is purely environment, because test-retest, obviously they share the same genetic material because they are the same people. Monozygotic twins share the same genetic material, so this gap in identifiability is environment. Whereas this gap between monozygotic and dizygotic twins is actually due to heritability since they insert 100% of the genetic material and dizygotic to insert 50% of the genetic material. For the sake of time, I'm not going to explain you about how we improved the ACE model so that it accounts for errors in the measurements, but if you are interested in this matter, it is really fascinating, and I'm looking forward to discussing it with you. I want to thank my group. This is not my work, it's the work of a great team, and if you have any questions, I will be happy to answer.